All right, good morning, everyone. Thank you for joining today's webinar, or actually good afternoon for the guys in America, and thanks for joining us on your late afternoon. This is a three-part series of ICM around the world, and Australia is the first cab off the rank. So we're really excited to bring this webinar to you. And personally, I'm actually really excited about this webinar because it's the first time, I think, in Australia that we've done both sewer and stormwater in the same presentations. So first one for me and a first one for InfoWorks Australia as well. So without further ado, let's introduce our guest presenters. So most of you probably know me, or the guys in the stormwater world would. I'm Sophia, I work for InfoWorks and I'm one of the water resources engineers here, mostly focused on the stormwater and flooding side. We also have Troy, who has 25 years experience with large-scale civil engineering design and construction projects. He has a proven track record delivering public and private projects across mining, municipal, industrial, commercial, educational, correctional and health sectors. Troy combines technical skills with extensive industry knowledge and has a passion to produce high-quality, cost-effective and sustainable infrastructure solutions. So Troy, thanks for joining us. And you'll get a couple of minutes to chat to everyone in a minute. And we also have Rosario, who's a senior engineer from Water Corporation of Western Australia. He works in the network optimisation sector as a civil engineer specialising in hydraulics. He has been working with the water and wastewater models for 15 years. His interest in modelling studies developed early while a student at university in Italy, and subsequently while working in the UK and then in Australia. So guys, thank you so much for joining you. I'm really, for joining us. Really excited to have you both, and it's nice to not have myself presenting today and to sit back and relax with the rest of the audience and learn from the professionals. Just before we get started on the presentations, a little bit of housekeeping. We really want lots of engagement from our attendees and our audience today. So if you do have questions along the way, please drop them in the questions box. And what we'll do is we'll have a little break during the presentations and get some of those questions answered from our guest presenters. And then also at the end of the two presentations, we'll also go through some question and answers. Also, if you have any comments or feedback, or you want to be a presenter on a further webinar or water talk, feel free to put that in the questions and we'll get in contact later on. I'm now going to hand it over to Troy, who's going to tell you a little bit about his company, Infra-Struct, and also his experience with ICM doing surface water analysis in mining and also sizing complex hydraulic structures. So Troy, I'll hand over the controls to you.
Thank you, So. And thanks for the opportunity from yourself and InfoWorks for us to be able to share our experience using the ICM software and the work that we've done on the particular projects that we're going to talk about this morning. A little bit of an intro on Infra-Struct and who we are and what we do. We offer infrastructure management, engineering and construction services, as explained there in my bio, to both the mining and the municipal sectors. Our primary point of difference that we strive to provide our clients is a one-stop shop turnkey solution where we can take a project from a single CapEx budget line item right the way through to a functioning piece of infrastructure under a single engagement. Our passion to provide that service is based on many years of experience observing other large organisations delivering such projects under relatively cumbersome models which comprise multiple consultants and multiple contractors throughout the project delivery life, which tends to not always produce the best possible outcomes and can be an expensive and time-consuming process, as well as an in-house management nightmare to administer all of the various procurement arrangements with the suppliers. So at Infra-Struct, we're passionate about what we do, and we're passionate about doing it right. And in order to do it right, we need to use the right tech, we need to use the right equipment, and we need to have the right people driving those tools. Hence, our approach and endorsement, I guess, of the ICM software in the services we provide. We find it a very valuable toolkit, and it complements the other tools that we use to provide our service. And very excited to be able to share a bit of what we're doing with that here today. The first project that I would like to talk about is a large mine rehabilitation project that we're looking after in central Queensland. Essentially, I describe the project and dub it as the wedding cake project. The mine that we're working on is a metal ferrous mine. It's previously been run as an open cut operation and now is significantly underground. As part of that open cut operation, large waste rock dumps of overburden material were deposited adjacent to the mine site. And our client is now, as part of their progressive rehabilitation program on this site and various other sites, are returning those waste rock dumps to sustainable landforms, which will ultimately be handed over once mining has ceased on the site. So essentially, the time-lapse image you can see on this first slide is a good all-encompassing capture of what we're doing, where we're taking the existing waste rock dump and reshaping it. The material that's contained within those waste rock dumps has varying levels of potential acid-forming material, which needs to be capped with a non-acid forming material for that long-term sustainability and handover. That landform that we reshape the waste rock dump into, it needs to be free draining, and hence the need for a surface drainage system to be designed and our use of ICM to do that. Moving on to the next slide, this gives a bit better visual, a little bit trigger happy there. This next slide gives a little bit better visual of the final landform that we're reshaping to. So the grey image you can see there is the final surface design with the surface drains burnt into that surface. And that image represents the machine control final design surface that gets loaded up for construction. And to the bottom right, the image and then the visualization of the ICM surface water model that we used to design the benches and also the chutes conveying the flows down to the receiving waters. Just a couple of project stats, I guess, before I jump into the detail, just to sort of put the project into context. The overall footprint of the site we're working on is 2.3 kilometres long by 1.7 kilometres wide. The height of the dump that you can see in that visualisation image there is approximately 100 metres high. All up, the project duration will span 2.5 years with 6 months remaining. A total of 3.5 million cubic metres of dirt will have been reshaped and moved, including the potential acid forming material being reshaped and the non-acid forming material being locally won and imported across the landform. It's a total of 750,000 square metres of reshaping and trimming to profile, which is 75 hectares. The contributing catchments which we have considered and modelled using the ICM package come up to a total of 405 hectares. 4 kilometres of surface drains have been designed and are being constructed. with the largest of those surface channels conveying 58 cubic metres a second as a design flow. All up, 90,000 tonnes of rock scour protection, which is being imported from a quarry approximately 100 kilometres from the site. And the non-acid forming capping material, which we're locally mining within the site, will ultimately produce an expansion of 550 megalitres to the site's sediment and storage, surface storage water systems. So for this project, we considered direct rainfall modelling as an essential approach, and primarily that was on the basis of the scale of the project, our desire to iterate the design efficiently in order to optimise it, given the large quantities and large costs involved in the project. But more particularly, in order to get an effective and efficient earthworks design, we needed to vary the longitudinal fall, the width, and the cross falls of the benches to create the final landform, so that we could minimise the amount of material that had to be shifted to create that final landform. So from many years of experience designing surface drainage systems, for me, it was a no-brainer that we had to use direct rainfall, because it would be almost impossible on a site as large as this to predict where those critical points will be in those benches, given that the benches may go from a relatively wide cross section through narrow sections, wide again and narrow again to the receiving channels, and those longitudinal slopes will vary throughout that full length of those benches. So it gave us enormous power to be able to import our high quality surface designs into ICM and analyse those with a high degree of accuracy, and measure freeboards that were available, so that we could optimise the length of berms that were required along benches, and we could size the various channels that were required to take those flows down to those receiving waters. Adding to the mix there, that given the relatively man-made shapes of the catchments and steep slopes and versus flat slopes of the benches, partial area effects were at the forefront of our mind in using, other more traditional sort of manual approaches, and potentially getting that wrong, given the large flows and the high potential for erosion should the benches overtop and damage the batters. So in order to leverage the tool, the ICM tool, to its maximum capacity, we saw opportunity in extracting large amounts of results using the result extraction functions that ICM has. So what we wanted to do was set up result lines, as you can see in the image on this next slide, at close chainage intervals along each of the drainage features, so the benches and also the chutes. That allowed us to run the model and in a relatively quick time frame pull out results at every one of those locations, import them into a purpose-built calculator, which we constructed in Excel, and we were able to automate the design process of the benches and the chutes within that tool that we constructed. And that allowed us to measure what freeboards we had at each of those result line locations. If it was insufficient, we could then redesign the surface accordingly. And if we had surplus freeboard, that may in fact allow us to reduce the size of drains or reduce the extent of berms or benches that needed to be provided to convey those flows at that particular location. So given the quantities and the cost, that was a massive advantage to the project. But But what that needed is some clever sort of sequencing of the works so that we could do that in an efficient way, and get those great results. So what we came up with was we had an initial finished surface design across the dump without the channels in position, and we came up with a methodology whereby we could quite quickly cut essentially slots within the final landform where we proposed these large surface drains to be positioned to convey those flows down the dump and to the receiving waters. The average slope of the batters is in the order of sort of a 1 and 3 slope, which is very steep to contain these large flows at sort of stable velocities to prevent sort of scour and damage to those drains in extreme events. So we positioned the, if you like, the slots in the positions where we wanted the design channels to be. We had the result lines then superimposed within the model so that we could run the model and extract design flow rates at those various locations, run that through our automated tool, which gave us then design sizes of the channels. That tool we used in a relatively clever way to optimize cost, whereby we use the multi-variable solver in Excel to solve the channel geometry in order to minimize the cost based on the actual cost of the construction activities at that particular site. So given that the scour material needed to be imported from a quarry via road train some 100 kilometres away, there's enormous cost in that particular component of the construction, as well as the size and configuration of the rock to be safely handled on such steep batters. So the selection of the channel geometry was primarily driven by safety factors and also minimising cost, whilst satisfying those drainage outcomes that were required for the project. So having extracted the flows via a relatively automated process from the model, having sized then the surface drains that were required by optimising the cost, we were then able to produce a final design surface within using the 12D design product software, and re-importing that finished surface back into ICM to validate that design. Again, the result lines are still in the model, so we can very quickly and efficiently re-extract results at each of those locations that we've previously created in our purpose-built design tool. We can compare what those final flows were to what the original assumptions were. In some cases, drains shifted in order to optimise, catchments were redistributed to optimise. So that gave us the ability to just iterate as many times as we needed to in order to get that final optimum solution. Ultimately, what happened there was it was about 4 iterations all up, and you know, we found that to be very workable. I'm a big fan of the 2019 and the AR&R ensemble approach. I think looking at design envelopes is a very sensible approach to drainage design, given all of the variables that come into play in such solutions. So we didn't find the run times that were necessary on this project to be obstacles. We simply just scheduled our work accordingly. We're running the models overnight, analysing and refining the designs during our working days, and if needed on that particular project, given that it's a remote location, we were able to run models in the off time, given that we were on a fly-in, fly-out 9-5 roster, where 9 days of working and 5 days of rest. And in those 5 days of rest, that provided a fantastic opportunity that if we did need to run models, we could do that at basically no cost to the program or the schedule. I guess another big advantage on this particular project and for our company is we're also running a Trimble Stratus drone, which we fly monthly LiDAR surveys of the entire site. Using the ICM software in conjunction with that functionality and that data that we're producing, that enables us to run a live surface model of the project and predict any potential scour locations or water management issues that we may need to take account during construction, which is particularly valuable at this particular site, which is at the northern end of Queensland and subject to the sort of monsoonal wet seasons that Queensland experiences during sort of the months of December through to sort of the end of March. So we've found that functionality and that capability to be super helpful for the construction team and for sequencing the works in order to minimise damage to the works as we construct. The extension to that is that we are able to and will be providing a full as-built ICM model of the final product to validate that the design objectives have in fact been met on the ground, which has been very pleasing to our client, given that they will ultimately be maintaining this infrastructure until the mine is closed, which is not scheduled for several years from now. So to wrap up on that particular project in this last slide, ultimately this is the final design plans that you're seeing with the surface channels designated with the required rock sizes to manage those design flows and keep those velocities sustainable, which again are validated through the final ICM model, the direct rainfall model. Just to give all of the listeners out there a bit of a context to the drain sizes, we're typically averaging between 10 to 15 metres wide. Longitudinal slopes down the batter faces, as I said earlier, are around 1 and 3. The pink shading represents a D450 rock scour material, which is ranging in particle size from 100 millimetres right the way through to 900 millimetres. The yellow stripes that you can see across the drains in the batter sections are actually keyed anchor blocks, where we've used a 1 metre diameter rock in series across the drain cross section to anchor the scour material to the batter. And the blue shading there indicates a D700 rock, which is varying from 100 mils through to the 1 metre particle size. So it's relatively large scale open surface drains that are quite difficult to construct on those slopes and very expensive. So channel profile and overall construction quantities were of primary focus to make sure that the design was optimised to minimise those outcomes. So in summary there, the outcomes for this particular project using the ICM software to underpin the design was the bench and bund surface profiles and measuring the available freeboard for the various design AEPs that our client had asked us to consider and cater for. The product that was produced out of that design was a 12D design surface, which we were able to both validate in ICM from a drainage outcome perspective and directly use to load up in the machine control earth moving equipment that's being used within the site, that is generally delivering that tin on the ground plus or minus 25 mils, which our own internal drone survey function is able to measure and produce a DTM for us to validate, again within that plus or minus 25 to 50 mil tolerance, which we're finding 9 times out of 10 we're closer to that 25 mil tolerance, which is just fantastic when we're coupling that up against the 2D direct rainfall approach. Rock scour protection was then able to be specified and sized, and manage the quarry arrangements to service the project, and ultimately we aim to land at a complete overall site as built surface or tin, which we'll be able to validate again through the ICM direct rainfall approach, so that we can validate that the design objectives have in fact been met on the ground. One other project that I'd like to just briefly touch on is an open cut coal mine, again in central Queensland, that we've been involved with, where we've helped the client understand the immunity that they currently have to some underground portals. So this particular site initially was viable under an open cut approach. Once that resource had essentially been exhausted with the open cut methods, there was a large resource remaining, which was accessed via underground portals, which can be seen in this image through the open cut high wall. The challenge there was that a large river passes adjacent this site, and in previous years and relatively large events, there has been overtopping of that river into the pits, and ultimately putting the asset and the mine at risk with inundation and damage. So this particular project, we used the direct rainfall method, but also in conjunction with a raft subcatchment hydrology instead of the direct rainfall method. And we did that because the ground data was available to us at 10-metre contra intervals, and we were able to easily delineate catchments at this particular site. As you can see by the image, the open cut overburden crests and the high wall tops and toes, so on and so forth, were fairly easily definable. The catchment, as noted there, was sort of in the order of a square kilometre, and we had the benefit of previous studies and calibration points to validate the model. I guess one of the key considerations is always importing the or reflecting the surface to be modelled within the direct rainfall model itself, and making sure that we've got a good representation there. We find with the point cloud data that we're able to produce out of our drone surveys and the LiDAR information that's typically available at these sites, we can get a very good representation, which is sufficient for the levels of accuracy that we're working to. So in this particular project, we've given an example there of the cross section that has been produced within the model, and we've got awareness of where that is accurate or deviates away from an acceptable accuracy, and if need be, we just simply adjust the tin accordingly to improve that reflected surface that we're modelling. Ultimately, this project, in terms of deliverables, we were able to provide inundation maps to the client where they could see areas that were potentially at risk. We were able to quantify what freeboards were currently available, and we were able to define what works could be provided on the ground in order to provide the minimum standard of immunity that the client was after for those particular portals. And that about wraps up the technical run through of the two projects that we've used the ICM software for effectively. And I'll hand back over to you, Sophia, and for the next presentation.
Thanks, Troy. You made a joke this morning that you could talk for hours on this topic, and I don't disagree. I reckon you could talk for days. You know it so well.
I was trying my best to squeeze that all in, so yeah, hopefully
you
I
did
didn't
well.
run too far over.
No, you're good. Big project, and not a lot of time to cover it all. You do have quite a few questions that are coming through. Some of them you've actually already answered, which is good. I thought I might just ask you a couple, and then we'll move on to the sewer presentation.
Cool.
But we've got someone here wanting to know, was there any water quality modelling happening as part of this project? Or was it
Yes.
just about the scour?
Yes, the water quality modelling on the site, the site itself encompasses quite a few mines at different locations. So there is, under another department and another consultant, there is extensive water quality site-wide modelling, which we were interfacing through throughout the works that we're engaged to do.
Perfect. And another question, what was the largest rock that could be practically moved on site when you were sizing the rock for the scour protection?
Ultimately, we arrived at, so what we did is we looked at the size of excavators that we had mobilised to the site, because there's a large cost in mobilising equipment to those remote locations. And the product manufacturer's specifications are fantastic references in those particular cases to evaluate slope and handling capacity. So we have a CAT 336 excavator doing most of the rock placement up there, and it can safely manage a 1 tonne mass, which we converted back to a 900 mil diameter rock based on the specific gravities that we measured at the quarries which were supplying the rock.
All right, that's it's not a small rock.
No, it's not a small rock, but they're not small flows, and it's quite it's been quite you know, an insight throughout construction. We've seen 2 wet seasons, given the duration of the project is 2.5 years, and you know, the erosive force of water at those slopes, you know, just drastically can't be underestimated. So we're the bigger the rock, the better from our perspective.
I bet. Okay, what we'll do is we'll move on to Rosario and the Water Corp presentation. But guys, Troy is going to be here till the end, I hope. And so
Yes.
If you've got more questions, or if we haven't answered your questions yet, we'll see if we can get to them at the end. So I'll just give the mouse controls to Rosario. And Rosario, you've been sitting patiently and quietly waiting for your turn. Thank you for joining us. So Rosario is from the Water Corporation of Western Australia, and he's going to talk about actually a really exciting project, something that I've never even thought about or learnt about, which is optimising sewer operations at a wastewater treatment plant. So good morning, Rosario, and thanks for joining us so early. I know that you're at 7:30 a.m. for you.
Yeah. Good morning, everyone, and thanks for inviting me. So I work for the Water Corporation of Western Australia, and which is the main service provider of water and wastewater in the whole of Western Australia, basically. And I work as a senior engineer for the network optimization section. Now, this section focuses on conveyance, both to water and wastewater. We run optimization projects where optimization means sometimes energy efficiency, and some of the times, most of the times I would say, it's more about deferral of a capital project. So to do that, we tend to use models a lot, as we need to do operational modeling in order to achieve few more years out of our current network. I'll move to the next slide if I've got control. Okay, so enough of me and the Water Corporation. Let's talk about this project. So the project is based in Banbury. Banbury is a town a couple of hours south of Perth and 1 hour north of Margaret River, which are well-known areas as well. And it's a growing town. it's next to the Indian Ocean, and its water treatment plant discharges into that. It's also a tourist attraction as people drive into town to swim with dolphins on a regular basis. It's quite a unique environment. So the treatment plant services a total of 42 pump stations. And moving into the next slide. So it's very slow for some reason. So the issue is with the capacity of the wastewater treatment plant. So Sophia, I can't change slide.
Zoe, I am going to be your admin person, and I am going to move slides for you when you ask me to.
I'll ask you. Yeah. Okay. Yeah, that's better. So I was saying that the treatment plant has got a nominal capacity of 700 cubic meters per hour, which, if exceeded, will determine a shortening of the processes times within the treatment plant, which then causes poor performance at the treatment plant and a poor discharge into the Indian Ocean, which can also put us in trouble in terms of operating license. That doesn't happen regularly. So on a weekly basis, we are within, on an average, within the limit, but on a few days over the week, we exceed these limits. We need to say that Banbury runs a separate system. So obviously, although there are some inflow and infiltration components, they are not really relevant to the problem. So obviously, the upgrade of the treatment plant requires a substantial capital investment, and the idea was to try and see if we could actually flatten these curves and avoid, so defer the capital upgrade. And at the same time, if we could store water within the system to then discharge it into the treatment plant for a flatter inflow hydrograph into that, we would then greatly improve our processes and the energy consumption within the site. So there's a number of advantages related to a flatter inflow hydrograph, if that can be added. If you can move to the next slide, please. So back in 2014, we were concerned with wastewater overflows. So we introduced this project, the wastewater overflow risk management, which we call WARM. So that was an enhancement to our sewer pump station so that they could be remotely controlled from the operation center. So without anyone attending the site, we introduced this technology that allowed us to change the control settings, so the car-in and car-out levels of sewer pump stations. And another interesting aspect of that is that we could introduce up to 24 different set points in a day, and this could change also daily. So, so basically, this give us a dynamic control over pump stations, which we can use to manage overflow risk across our network wherever we deploy these technologies. So the idea is that having this technology in the background, we could actually use the wastewater network as a balancing tank to try and store flow where possible to reduce the peak into the peak inflows into the treatment plant. So to do that, obviously it's a complex system of 42 pump stations. We have to find the optimized combination of variable levels across all of these pump stations at the different times to achieve the best possible solution. So if you can move to the next slide again. So the process was obviously model-based. So we started with an ICM model, and the first thing that we did was to calculate time to overflows for as hydrographs using the model for all of these pump stations. And then we would also look at where connections were to avoid excessive surcharge. That would determine basically through the model what's the maximum allowable level that we could attribute to each pump station. So that is obviously over the normal carrying level, and then therefore that would be the interval where we could determine options for each pump station at the various times to operate. So the model was, we introduced an RTC, which determined 12 blank periods as it ran inside the network. Now, the reason for doing that is that we would then use Optimatics to actually pick the operating level options and test them on each period, on each pump station until it finds the optimal solution. So that was sort of the process we thought of. And we would basically set an outflow objective as a test of for the solution to see how good it was. So if we can move to the next slide, this should become a little bit clearer. So we got a model. Again, we developed these options for optimization as a desktop study. We had Optimatics running a number of iterations, trying all sorts of options at the various pump stations at different times. And then this would create some solutions. We would pick out of 20,000 solutions per iteration run, the best ones, load them back into the model so we could check them, learn from them, and then instruct Optimatics for another series of iterations to keep refining the solution until we were happy with something. And so the penalty, the objective function created a penalty every time 350 kiloliters every 30 minutes were exceeded. The other thing is that there was a cost associated with the use of each pump station, so as a balancing tank. So fundamentally, we wanted to minimize the number of pump stations that we would use. So there was a cost associated every time a pump station would store water. So if we can move to the next slide, please. So this is the Pareto front coming from the Optimatics software. So you can see that it's a funny Pareto front. So there are vertical lines. Each vertical line corresponds to the same number of pump stations which are used as balancing storages. And you can see that to a certain point, as we make the solution more complex, we've got an improvement in the solution. So we minimize on the y-axis the inflow penalty, but above a certain number of pump stations, we don't really keep improving the solution according to the software. So the red solutions are good solutions that the Optimatics software suggests us to look at for various reasons, and so we loaded them back up into InfoWorks, and then we did some engineering judgment and some final refinement to come to the final solution. So if you can move to the next slide. At the end of this process, we created we picked a solution, and we delivered an operating manual, which essentially contained carry-in and car-out level settings for each sewer pump station that we would use. We used 9 of those in the end, and that went straight to the control room. And then we provided the region with maps showing the maximum level of surcharge that they could expect as we run the system in this way in their system. So, and that wraps up the project.
Thanks, Rosario. We've got a few questions already, and I think this one came through. I'll just go back to I can go back to the first slide. This one here, I've got a question here. Is the peak system loading for wet weather or dry weather?
Okay, so this is dry weather. In wet weather, so again, because it's a separate system, there's no big difference between wet and dry weather. We were not too worried about additional flows in the wet weather because there's more dilution, and so the actual treatment process is less stressed in its process. So we didn't have the same problem as in dry weather.
Okay, and another question, how much money do you think that you saved going through, you know, an operations method rather than doing capital investment?
Fundamentally, it's from a capital perspective, it's a deferral of approximately $4 or $5 million for a few years. So we would spend this money, but we are just buying time. On the other end, there are some savings in operational cost, particularly the energy profile. I'm told is better now at the treatment plant.
So definitely a good way to go.
Yeah, it's
buying your time.
It's marginal. Yeah, it's marginal gains in the big scheme of things, but they actually make the difference when you've got a capital budget to deal with.
Absolutely. And another question here: has the revised on-offs been implemented already in the real world, and have they been tested?
So we've done some tests in smaller systems to verify that it all works. We are currently deploying the warm functionality in some of these pump stations. So the full solution has not been implemented yet, but it's been partially implemented so far.
Sounds like you're well on your way. Is that something that you're going to do at other wastewater treatment plants, or do you not have the same problems?
We haven't really looked at it anywhere else because there was no driver for it. But I guess it's important for us knowing that we've got this methodology now that we can adopt elsewhere.
Yeah.
So, yeah.
I can imagine that people from other states and from other water utilities or other parts of the world would be really interested in that and seeing if they can implement it in their regions as well. Well, I'll open up the questions to both Troy and Rosario, who will be on here for a couple more minutes. Troy, if you're there, I've got one more for you. I find my spot. So we've got a question here. How confident are you that the rock chutes will stand up to the high flows in practice?
Well, based on the modelling that we've done, we're very confident, and throughout the design process, we can understand using the AR&R 2019 ensembles, we can understand that the range of design of those chutes have been sized in order to handle. So, yeah, we're very confident that the design is suitable for the AEPs that we've been requested to cater for.
And Infra-Struct doing the construction of the chutes, are they, Troy?
Yes, we're looking after the design and the construction and the overall management of the project.
That's good. Good to hear you're confident. Another question, was that the 1% AEP design, Troy?
So on the dump itself, we're looking at a 1 in 20 year design storm, and for the perimeter drains, which maintain or contain the flows within the current mine lease, we're at a 1% AEP.
I just realised asking questions for both a stormwater and a sewer project leads me to all sorts of trouble because it's quite similar terminology. I think I'll try and hopefully get the right questions to the right people. Rosario,
Yes.
any considerations to potential long-term effects of regular surcharging networks or pipe conditions and surrounding soil conditions?
Yeah, so obviously the other component is a worry, and we are actually working on it, as we experience already very high levels of H2S and a number of other complaints. But the large majority of our pipes are plastic or reline. So in terms of corrosion, we are already past that point where we put in mitigating solution in place. So it's more about managing customer complaints by reducing levels of surcharge as much as we can. If that makes sense.
And someone's asked if you've got don't you have an emergency relief at the pump station?
Yeah, we do.
Yeah, that goes. Does that go into the Pacific Ocean though?
Oh no. There are different. Yeah, there are. It depends. So each pump station has got different. But anyway, we are far from overflowing the pump stations. So the first activity was to determine time to overflows, and we've got some strict criteria of 3 to 6 hours minimum time to overflow at each pump station, and we never exceeded that in the project. So we're only really surcharging where we've got plenty of capacity in the system left, and yeah, we don't risk overflows in catchments.
Perfect, makes complete sense. We've got a couple of minutes left. I've just realised there's a lot of people just making comments that they would love a copy of your presentation and any more information that you've got, both presentations, and Rosario, if you've got anything that we could put up on your project on our public website. Everyone's quite interested. So I'll talk to you both about that after this, and let everyone know when the presentation's available for viewing. So we'll wrap up right on the hour. Firstly, thank you so much for Rosario and Troy for joining us, and thank you for all the attendees for all your questions and for listening in and learning about ICM around the world. Alrighty, well, I'll wrap it up. Hopefully you've enjoyed this morning's webinar, Water Talk, and I hope you've learned a heap. I certainly have. And we'll see you for the next one in the USA. Have a good day, everyone.